You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Richard Jacobs with the Future Tech and Finding Genius podcasts. I have Robert Munro. He's an author. He's an expert in combining human and machine intelligence. He's founded several AI companies and built some of the top teams in artificial intelligence. He's got a very diverse background, which we'll kind of go into, and he'll note as we speak. But Robert, thanks for coming.
Thanks, Richard. It's great to be here today.
Why the fascination? I mean, a fascination with AI is very understandable, but combining human intelligence and AI is a little bit of a different flavor. So, how did you get to that realization that would be a good way to go? And tell me a little bit about that.
I got to the realization that is a very important piece of AI is that the data side of things. Really looking at a lot of deployed real-world AI. So when we look at machine learning algorithms that have been used in industry today, almost all of them are powered by thousands or sometimes millions of human annotated data examples. So for example, autonomous vehicles know how to navigate down the street because thousands of hours of driving has been annotated by people to say that this is a pedestrian, this is a car, this is the lane, which is the middle of the street, this is a stop sign. And what this means is that in many cases, the quality of the data is more important than the particular algorithm itself when it comes to getting accurate and widely deployable machine learning. So that's what led me to the fascination with machine learning. And then in terms of writing a book about it, it was really plugging a gap. So if you look at most machine learning courses at universities or online, or even most books which are out there, they'll only teach the algorithm side of things, not the data side of things. So a lot of data scientists get a rude shock when they start trying to do real world AI for the first time, and they find out that they spend more time managing the data and getting the right human annotations than they do building the algorithms themselves.
Did you write the book, or did a machine write it?
We are a long way from having a machine that could write a book like this, unfortunately.
Well, when you talked about data being clean or useful or better, what does that mean? How can you get good data, and how can you get data that's not good? And what makes the difference?
I mean, that's a great question, because good data is incredibly hard to get. And unfortunately, it's often looked at as a problem in machine learning. So I think this bias of focusing on algorithms still carries over to industry a little bit, and people want to outsource the problem of getting good data, or think it can be easily outsourced, so that's a trivial problem. And unfortunately, none of those are true. And I think that's a real shame, because the data side of things, like I said, it can increase the accuracy more than the algorithms themselves. And also, it's just an inherently really exciting problem. Like, this is how humans and machines are working together to create accurate models that can be deployed in the real world. And so in terms of the different aspects that you need to consider, one is simply having the data. So for example, if you're deploying an in-home device and you need good speech recognition, if you don't have thousands of hours of recording in all the languages you care about, there's nothing that algorithms can do to overcome that. So you just need that raw data to begin with. And then the other piece is you need quality annotations on that data. So if someone is transcribing your thousands of hours of audio in order to teach your home device, which of those thousands of hours are the most important if you don't have the budget to transcribe all of them. And what happens when multiple people disagree with each other? So you might have 2 people or 3 people transcribe the same sentence and come up with slightly different transcriptions. And it turns out that the math, in order to figure out what should be the correct answer when humans disagree, is just as complicated as any of the math, which is in the algorithms themselves. So it really is a fairly complicated specialization of computer science.
Wanted to, have a really amazing translator, and I have tons of data. What makes the data more usable than not? What have you observed, or have you figured out any techniques on how to look at data, look at an algorithm, match them, and say, all right, let's go back to the data instead of the algorithm and see what we can do to either add more or change what we're putting in there, maybe trim some, etc.
Right. Yeah. So that process you're describing, looking at where your algorithm is today and whether it's accurate or not and what's missing, that's known as active learning within machine learning, and that's one of the main parts of my book and one of the most exciting areas. And you can think of active learning as the process of trying to decide which is the best data for humans to review to increase your model's accuracy, and then you can divide that further into 2 kinds of problems. One is things that you know that you don't know. So this is your machine learning model telling you that it has low confidence, for example, in a given translation. To continue that translation example, you might see that the model itself is telling you that it has low confidence every time these certain kind of words have been encountered. And so then that tells you that, okay, I need to go and get more examples of these kinds of words in the 2 languages that I care about, get examples of the sentences with that word translated, and that's going to improve my model. And so that's known as uncertainty sampling. And there are a lot of different algorithms for interpreting when your model is uncertain. And depending on your use case, 1 or more of those might be the one. And so that's a fairly straightforward way of deciding what's the best data to annotate, looking at where your model is currently confused. But then you have the much more difficult problem of when your model is getting something wrong, but it doesn't realize it. So it might be highly confident that it's getting a translation right, but it's not getting that correct. Or you might be working from a cold start, so you don't have any data translated between languages first, and you want to work out what is the best and most diverse set of data to begin with. And so the set of strategies to find out what your model doesn't know that it doesn't know, that's known as diversity sampling. And there's a real range of techniques to try and work out where you do have those gaps in knowledge. And they're important for, especially when you're adapting your machine learning models to new use cases, or when you want to ensure that you have real world diversity in your data. So your raw data might not be representative of the demographics that you care about. And so you'll want to employ techniques to make sure that as much as possible, your annotated data can be representative of everyone that is using your application.
What walls are being run into, even with all the best knowledge, combining your knowledge and, the best algorithm makers, where are the stumbling blocks and why do you think they're there? And maybe look at translation, or what area are you familiar with most that you could talk about?
Yeah, I mean, I can talk about a number of different areas. So my PhD was in natural language processing across a wide range of language use cases. I also ran product for AWS's first NLP and translation services. But I've done a lot of computer vision work as well, so I'm happy to talk about all these different kinds of use cases. What's interesting is that they all face very similar problems. So whether it's an autonomous vehicle deciding which data to annotate for its video cameras, or someone looking to translate between new languages, these same principles of looking at where your model is uncertain and trying to find new examples of data that you haven't seen before, they're all consistent across these different machine learning use cases. So most of the time when I've seen algorithm hit walls, the easiest way to get more accuracy is with better data. So we've seen some great advances in translation with the move to neural-based translation systems in the last few years. And it's been a particularly nice use case because they've been getting much more accurate with less data. It used to be the case say 5, maybe more like 10 years ago now, that the translation algorithms got better with more data, even if that data was really messy. So you could automatically scrape websites, look for websites that have been translated into different languages, programmatically align those different languages. And even though it was noisy, that would still help your machine learning model. So that was a huge advantage for widely spoken languages like English and Spanish and Arabic and Mandarin Chinese. With the neural approaches to machine translation, they're a lot more sensitive to bad data. So rather than looking at large volumes of data, you're better off having a small, very carefully curated data set. So this is a huge advantage to the 99% of the world's languages which don't have lots of resources out there. So this is really promising in terms of being able to think about good translation or good machine learning in general as a data problem.
Language translation, how is it being handled by Google and some of the top firms? Because let's say I'm going to just say there's 200 languages in the world. Specifically, what if you want to translate, Vietnamese to, Nigerian? Do you need direct data for that, or can you get it? Can you make it work by having enough pairings of other languages and the algorithms being sophisticated enough that they can do that? They can make that jump by themselves.
Yeah, that's a great question, because there's been some really interesting innovations there. And so, just a point of clarification: there's about 7,000 languages in the world, not 200. So there's a huge variety of languages, and I would say for almost every one of those 7,000, at least one of the speakers owns a cell phone, and so they have things like Siri or S-Voice or other language technologies on their phone. They can use search engines. They need spam filtering. And for the overwhelming majority of those languages, none of those technologies exist. Not translation, not spam filtering, not accurate search, certainly not voice recognition. So it's a real gap there. So anyway, back to your example. For every single pair of those 7,000 languages, 99.9% that there probably doesn't exist that parallel data. And so if it was between Vietnamese and a language spoken in Nigeria like Hausa or Yoruba or Igbo or one of the smaller languages there, you're almost certainly not going to find that parallel data. And so one of the cool things that we've seen recently, we're talking really just the last 3 or 4 years, in new neural approaches to machine translation, is that you can have one model that captures different languages at once. So it used to be the case that you would have one model that is trained on English and German and translates just between those languages, and another model that translates on English and French and translates just between those languages. And so if you needed to translate, for example, between French and German, and you didn't have any parallel data, you would have to put it through one model first, use English in what was called a pivot language, and then translate it into the other language. And needless to say, those errors would propagate. And they tended to propagate in a way that wasn't random either. They tended to compound and make that kind of double translation really useless. What's been really cool recently is what's known as zero-shot translation, where you can have one model, and all you're feeding this model is a sentence, and then an extra tag, an extra feature in that sentence, which tells you what language it is, and then a second token that tells you what you're translating it to. And then, so in that same model, one piece of training data can say, hey, this sentence is English and it's been translated into German. Hey, this sentence is in Vietnamese and it's being translated into Hausa. And then all of this is in one model, and then you can simply tell it which 2 languages you want as the source and the destination. So even though you've never trained on the particular pair, say, of Vietnamese and Hausa, the fact that you've got a lot of data in those 2 languages already means that the models do a reasonably decent job of translating between those. So that's just really exciting, and there's a lot of evidence that these models are capturing really interesting abstract properties across all languages. It's more than just kind of surface similarities. Although I'll say that with the caveat that these are normally used as a starting point. So I haven't yet seen this where those two languages are translated so accurately that you'd really deploy it in many situations, except maybe to get the gist of it. That's typically a starting point.
Is going to get us there.
And then you can start building it up. Sorry, what was that?
What do you think is going to get us there? And then maybe even the next step, a language that we have no data. Maybe an old language that was never understood in the first place. An ancient language that no one's been able to decipher. What will it take? And do you think at some point we'll be able to do that?
I'd love to see that. So it was an interesting paper out of MIT a couple of weeks ago, looking at what was a lost language, but we kind of reinterpreted about 50 years ago, called Linear B. It turned out to be a completely unique script for ancient Greeks. And they were able to show that some of these modern machine learning techniques could be used to partially decipher what are now lost languages. So in that situation, or for thousands of languages today where we don't have that data, these kind of models mean that we have a much better starting point. So it might have previously been the case that you needed hundreds of thousands or probably millions of examples of sentences in two different languages to translate between them. For a lot of these smaller languages now, you might be able to get to accurate models with maybe only 10,000. And so at 10% of that cost, you can create systems where people can start using this, and maybe the translation is bad to begin with and needs to be mostly manual to begin with. But as they use it in a relatively short amount of time, it can very quickly adapt to those new languages. And so that's super exciting for any smaller language community that wants to start adapting tools into the language of their choice.
I think, I don't know who has the biggest data sets of language processing. I guess Amazon and Google and a few others. If they combined all their data sets and looked at them, I would think that they would see a structure and a rule base for language, no matter what language it is, and therefore would be able to put that back into the algorithms. The algorithms, I would think, would find unseen correlations and maybe make this whole rule structure, and then we could move forward and translate anything to anything because we would understand that underlying, again, rule structure that's common to all languages.
Yeah, and I think it's a really good observation that you can just take a very large amount of raw data and start to get meaningful patterns out of that. So a little bit in translation, but certainly more so in other areas of natural language processing. This has become the most popular way of building machine learning. And so this is what's known as contextual models in this part of machine learning. It's not a really simple technique because obviously with this raw data, you don't have these human labels, but you can create tasks which almost seems like a human label. And so a lot of these contextual models are built on all of Wikipedia and all open books which are out there. And these machine learning models are given very simple tasks like predicting the next word in a sentence. So if I was saying something like the lamp is white, you would give this machine learning model the blank is white. And then it would try to predict, what word, what object falls in that blank space, based on all the available context. And so, having given these machine learning models this relatively simple task of guessing words and sentences, and then a similar one of guessing whether two sentences follow each other, we have these very large pre-trained models that really do encode, like millions and millions of sentences of data. And then they can be adapted to different use cases. So if you're looking in the NLP literature, you'll see these called contextual models or pre-trained models. And they, for weird historical reasons, go by names of puppets like Elmo and Bert. And so they've been super exciting in terms of, in a very short amount of time, these contextual models are state of the art in all kinds of language technology tasks, whether it's question answering, identifying the names of locations in text, identifying the sentiment of text. Really, in just the last 3 or 4 years, these kind of models have changed the way we're looking at a lot of language processing.
All right, so I've beaten you up on language for a while here, but what are some of the other areas that you see soon in the next 4 or 5 years we're going to have big advancements in the AI component? Will it be autonomous driving, or where do you think the big breakthroughs are going to come? What will they look like?
I think so. I mean, I've made some very public predictions about autonomous driving. really being launched in say the next 2 to 3 years, and so I hope to be right there. Yeah, so I think computer vision examples are pretty excited and very nascent right now. For a lot of use cases, especially things like search engines, we've had AI out there for like 15 years already. And so there's a lot of mature examples of AI applied to language across many different industries that have been around for some time. Conversely, there simply haven't been that many computer vision use cases out there. And it wasn't until recent advances in neural approaches and more than the algorithms themselves, just the ability of hardware to run at scale, that we had accurate computer vision models. So now that in the last few years, we have accurate computer vision models that can do autonomous driving in ways that we wouldn't have trusted 10 years ago, that can do other things like surveillance or predictive maintenance, identifying cracks in machinery, integration with robotics and then other kinds of reinforcement learning. It means we're really just at the start of looking at a lot of potential interesting use cases for computer vision. I will say that this is also one of the most overhyped areas of artificial intelligence. I don't know any computer vision focused startup in Silicon Valley that could honestly lay claim to yet having discovered a successful and profitable use case. So I think we're pretty early there at the moment.
Autonomous driving, you think definitely a good possibility that it'll really advance to where it's super useful and in use by many people. Any other areas? Well, how about an area that you think is really, really far off before we're going to get there? Is it general artificial intelligence, or is it other areas that are even much more tame but way, way off?
Yeah, so general artificial intelligence is way off, and no one's really working on it. Even people who say they are, it's more of a brand to get publicity and hype around their work. They're really thinking about AI. They're generally still working on scenarios which are really narrow in terms of their application. So a good example there, back in language data, is that for spoken language, for 99% of the languages out there, and even for most English accents, AI can't even tell you what the words are. And it's a little trickier than you intuit, because when you speak any language, you tend not to leave a gap between words, like you do in most but not all written languages. So it makes it a little bit complicated. Human brain's really good at that, at determining the gap between words. But AI is not so good at that for, I would say 99% of the world's conversations out there right now. And that's just trying to tell you what the words are in a sentence, when you already have a reference dictionary, let alone what the meanings are. So we're a long way off for any kind of autonomy. And so I would say that the biggest danger in AI, therefore, is not autonomous AI that could work outside its programming or become malicious in some way. The biggest danger is that bias in representation. It's that most people can't yet take advantage of voice recognition because we don't yet have that training data in their languages.
Well, very good. Well, what's the best way for people to find out what's really going on in AI? I mean, would it be reading your books or articles you put out? Like, what's your recommendation on how people can go further?
You should absolutely start with my book. That would be the right place for it.
What's the name and where is it?
It's a.
Tell me.
Oh yeah. So my book is Human in the Loop Machine Learning, and if you search Human in the Loop Machine Learning, that should be enough to bring up the book. It's published by Menin Publications. We're publishing chapters as we go, so I've written most of the chapters right now, and I think about half of them are already available online if you purchase the book. And then the hard copy of the book will become available once that's complete early next year. So that's, yeah, I mean, I'd certainly recommend my book, because like I said, it was the book I wish I had gotten very early on in my career. Like many people in my early career, I looked just at the algorithm side of AI and failed to realize for a long time that the data side was bigger and more interesting and more complex, and a lot more problems to solve. Beyond that, I think if you're interested in AI and you come from a technical background, A lot of the big conferences out there have really high rejection rates. So that the quality of research is incredibly high out there. And, most AI papers are written in a way that should be transparent if you come from a technical background. If you don't come from a technical background, I think it's going to be a little bit harder to see through the hype. Certainly, most of the news articles that we see around AI don't seem representative of our field to those who work in it. And yeah, unfortunately, I don't have a good solution for that.
Good. Well, Robert, thank you for coming on. It's been an interesting call.
It's been wonderful to chat today. Thanks for having me.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.